Moving on to section 8, looking at expected value. You will eventually be asked to create your own game, but before we get to that, we're going to be looking at a quick example of how to use dice to calculate different probabilities to invent a dice-based game that uses expected value to either be a good design for, let's say, if you're running a casino and you want to make sure that you always win as the casino, you want to make sure that you've designed it so that the expected value is in your favor. Vice versa, if you're looking for something to bleed away all your money to the players. So we have this chart here. It says outcome number 2 all the way through 12 and the probability of each. We want to be able to fill that in. In order to do that, I put in this chart here, so you won't have this, but we can just kind of follow along together. These are all the different ways that you can roll 2 dice and get different outcomes. So, for example, if your first one was a 1 and the second one was a 1, you would end up rolling a total of 2. Keep the first one a 1, the second one could be a 2. Keep the first one a 1, the second one could be a 3, and so forth all the way through. Then change the first one to a 2 and a 1, 2 and a 2, and these are all 36 possibilities for ways that you could roll 2 dice. So let's look at how much value each of them has. To get a 2, a total score of 2, this is the only way you can do it. That's the only one way that works, to roll a 2 out of 36 options. If you want to get a 3, you could do a 2 and a 1, or you could do a 1 and a 2. Now to get a 4, you could get a 3 and a 1, or a 2 and a 2, or a 1 and a 3. And you'll notice that this pattern continues all the way across this entire board. If you're looking to get a 5, you have all these options, and so forth, and it keeps increasing until you get to the most likely number, which is going to be 7. You can get 7 through 1, 6, 2, 5, or 3, 4, or any of those flipped over. So that's 6 different ways out of 36 to roll a 7. So we're going to fill in this chart. It's something out of 36 each time, and we want to make sure we fill that in. So our probability here is going to be 1 out of 36. Probability for the next one, 2 out of 36. 3 out of 36, and we said that that pattern continued all the way up until you get to your middle number. And your middle number in this case is going to be 7. So we get to 6 out of 36, and yes, that reduces to 1/6. For this case, I don't think it matters at this point. So then we're going to start counting down. 5, 4 out of 36, 3 out of 36, 2, and 1. And so now you have all the different probabilities entered in. Now I'm going to invent a game. I'm going to invent my own game to go with this video. You could invent any other game you wanted when you get to that part of it. For this, I want you to follow along with my game. And the way my game is going to work is we're going to pay out big time to the ends. So if you are on the ends, you're going to be a big winner, and if you roll a number in the middle, you're going to be a loser. So the payout means that for each one that you pay to play, for each time you play the game, how much will you win if certain things happen? So I'm going to say that if you roll snake eyes, you roll a 2, you get paid out 5, even though you only paid 1 to play. So you make 5 times your investment back if you do that. And I'm going to say that you get 4 for rolling a 3. So suddenly now there's lots of ways to win. And I'm going to say that you get a 2 for rolling a 4. And then we stop giving payouts on this end. I'm going to do the same thing on the other end. I'm just going to choose, because my game says roll an extreme number, 5, 4, and 2. And then we put in zeros for the ones that we aren't going to use. And again, these purple ones, there's nothing mathematical about that. That's just my personal choice. I designed a game like that. You could design something different in the next part of this. So I'm going to choose a color here for partial expected value. And what this means is take this times that. It means take your 1 out of 36 times your 5, which is going to be 5 out of 36. Means taking these and multiplying them. 4 times 2 is 8 out of 36. Does that reduce? Absolutely. For now, I'm going to say, again, let's not focus on that. Here you have 6 out of 36. 0. 0. Remember, 0 times anything is 0. Too far. Nope, nope. All of these are 0. And then we're going to multiply this one to get 6 out of 36. And then we're going to have 8 out of 36 here. And the last one we're going to multiply 5 and then over 36. So we zoom this out, we should have some roughly parallel patterns on both sides. The question below it says, in this example, what is the expected value? And the expected value is when you add up all these partial expected values together. So you have 5 and 8 and 6 all over 36. So we add those numerators and then we keep it all over 36. So 8 and 6 is 14. 5 more is 19. Now on the other end, I'm going to have the same number because of the way I set it up. So I'll have 19 over there as well. So I have 19 plus 19. And what that gives me is 38. So my expected value is 38 divided by 36, or 38 out of 36. So is this a good game for the player or the game designer in the long run? If you play this long enough, who would win? Me, the designer, or you, the player? Whenever the return here, this is the return for the player, whenever the return is higher than the house standard cutoff line, then you are going to be designing a game that's good for the designer. However, customers might not like it. So from my perspective as the game designer, if people still don't mind playing it, that's fine. But if I were to leave this open as a money thing, I would be losing money each time people play, because I would expect to lose money slowly over time with this. So again, it asks, is it a good game for the player or the game designer in the long run? That's going to be the player, because the player is going to have an advantage if I'm paying out more than I'm taking in. What is the expected value is literally where you take this and you turn it into a decimal if you want to. The last part says, why is it important to know expected value when people gamble on games of chance? It's saying, does this actually apply to anything beyond this particular example? And the answer is yeah. Anytime you are playing a game that involves some risk but has the potential to reward you, you need to understand how the expected value works. If you buy a lottery ticket, by knowing the odds of winning and multiplying it based on how much money you could win and how much you paid to play, you can find out what the expected value is in return. You can say, okay, yes, I only have a 1 in 200 million chance of winnings, but I could win $300 million, and I only have to pay $1 to play. If all of that were true, it would actually be somewhat intelligent to buy a lottery ticket. Again, not great odds, but if it does pay out, it's going to pay out quite well, and somebody's going to do incredibly well with that, better than the money invested. So you have to be smart. Not everything that has a good expected value is always going to be a wise purchase or a wise investment. but you need to know if playing the game for a long time is going to help you or hurt you. I can tell you that games of chance in casinos, any kind of business that makes money off of games of chance, I can guarantee you that they are all going to have expected values less than 1, as in a fraction where they keep more money than they give away. So I will let you choose your own specific answer to that, but hopefully that gave you some initial ideas of how to work.